In this video, I'm going to talk about the data collection and gathering phase of the PyVC protocol. But first, some words about precision and accuracy. Precision represents how repeatable the results are from any data set, and it's usually indicated by the number of decimal points that are reported. So, results can be accurate, but not precise, that is widespread, but close to the true value on the mean. Or precise and accurate, that is, the data is very tightly gathered and on the end very close to the true value. And we also have some bad cases, like the results are not accurate, not precise, so it's nowhere near true, and the data is spread all over the place. Or it could be precise and not accurate, that is, really tightly gathered data that is nowhere near correct. So we need to bear this in mind. Throughout this presentation, I'm going to be talking about aligning precision and accuracy of the data that we're working with. And this is what I'm referring back to throughout that discussion. So in part one of this video, I will talk about gathering element data. On the map, this is at the same level as gathering the climate data. These activities are highly integrated. They're done at the same time, but they may be done by different teams. This session covers what to consider when defining the system elements and ensuring that the system definition aligns with the assessment scope. The first thing we need to do when defining the elements is define the inventory of the system. We can't assess everything, so we need to set boundaries around the assessment, and it's project specific. We only consider relevant systems, not the entire inventory of the asset. Then we work with discrete systems, subsystems, and components. And we have several questions that we need to address. Which system are we working with? What elements are included? What's in? What's out? Where's this thing located? Are other jurisdictions affected? Who makes decisions about it? And what's it actually supposed to do? How critical is it? This is an important phase. Scope defines what's in and what's out of the project, and we break in-scope items into elements and sub-elements. Then we confirm the inventory with the owner. We verify our key assumptions and decisions to make sure that everybody's on the same page. And here is an example system breakdown. On the right-hand side, we can see a wastewater system. The wastewater system is broken down into a number of subcomponents: treatment, lift stations, sewers, outfalls, and odor control. And treatment, for example, can then be further divided down into pumps, the building envelope, and disinfection. So this kind of intellectual, logical approach is what we do throughout the process. We take a look at each system and break it down into reasonable elements and sub-elements that we can then use to address the objectives of the assessment. So the key points to take away from this: that scope management is important, and that system definition that we use draws on the scope, context, and criteria for the project. In part two, I talk about gathering the climate data. As I said previously, it's at the same level on the map as the data elements section. This work is tightly integrated. This session will cover choosing climate parameters, thoughts on establishing climate thresholds, the importance of matching horizons with the useful life of the system, and a brief introduction to likelihood scoring. So we need to choose relevant climate parameters. They need to be specific to the system, and we can collaborate with the staff of the system to identify previous issues that may have involved climate. So that helps guide our considerations as to what might be important for this particular assessment. It's system focused. So the more detail we require in the assessment, the more detail we may require of the climate. So as we get into very specific and detailed assessments, we may require the expertise of a climate specialist. Now, this is especially the case when we start encountering what potentially new climate hazards. And in that case, it is highly recommended that we refer to a climate specialist to get their expert advice. Now, we need to establish thresholds. Now, thresholds are tripping points at which a climate hazard causes an impact on the system. They depend on the system, and they can come from a number of sources. We could have a design threshold that's based on the design value and the standards. Or we could have empirical thresholds, things that we have seen cause problems in the past. And we may have multiple thresholds, service interruption and failure at a different level. So the same climate parameter, but a different threshold for service interruption and another one for loss of asset. So what do we do when there are no thresholds? There's no information in the literature, no empirical data from our experience, but we expect a relevant climate change event. We'll look at a range of reasonable climate projections. We'll evaluate the risk profile for each, and then we will assess which risk score is the most appropriate for this situation based on our professional judgment. So we need to match our horizons. We establish a baseline. That's usually based on 1981 to 2010. And then we align our future climate projections with the design life, the useful life, our refurbishment schedule, and we look at firm renewal plans. Do we plan to shut this system down somewhere between now and the end of the service life of the entire system? For a long service life system, we could have multiple climate projections. And we need to match our precision and accuracy. So we align data precision with the level of the assessment. Precision can be costly. Getting really precise results can be a lot of effort. So we reserve the cost of doing that for the relevant risks. Now, doing this requires some professional judgment. But typically, for a screening level assessment, we're looking at higher level data, not as much precision. But when we're looking at potentially serious risks, where we're going into a deep dive into the causes and effects of those risks, we may require much more precise data. Now, the climate team is going to be charged with providing us with a set of likelihood scores. We're concerned about the chances of the climate event happening, that it exceeds a threshold, and it's within the time horizons of the assessment. Likelihood scoring is an informed decision based on professional judgment. We like to validate it at a workshop. There have been times in the past where climate team has developed a likelihood based on all the information we had at the time. But when we got into the workshop, we found that we had missed something, or there was some information that we were not aware of that had changed that parameter. So it's worthwhile having that discussion at a workshop. The protocol suggests that we use a 5-point scale. Alternative methods are allowed, but we ask whatever methodology you use that you document the reasons why you chose that method. And here is an example of a typical likelihood scoring matrix. 2 approaches are provided for in this example. A descriptive approach based on word descriptions like negligible or occasionally likely, sometimes frequent, very frequent. This requires some professional judgment and some consolidation with the workshop team to make sure that we're all on the same page with what these descriptors actually mean. There's also a semi-numeric approach provided, which provides return period ranges that then can be applied directly to a likelihood score. There are several questions we need to consider. Are significant changes in the system expected over the horizon of the assessment? We expect to see something. What level of precision is needed? For screening studies, we may need more qualitative data. For a detailed assessment, we need something that is much more quantitative. And the key question is, are climate thresholds expected to trigger more or less in the future? So we need to put it all together. This is an iterative process. The system element team and the climate team are working side by side and in consultation with each other. So there's lots of cooperation between these two teams. It may take some time to fully define the elements and the climate parameters, but based on this consultation between the two teams, we'll end up defining climate hazards, threshold values, and likelihoods, which are then forwarded into the climate risk assessment in the next stage of the project. So the key points to take away from this is that climate data should align with the assessment scope. There are several ways to establish threshold values, and that likelihood is based on proxy analysis and professional judgment.